In this video, I'm going to talk about integrated rate law, and the law that I'm going to focus on is going to be the zero order reaction. And the points I would like to explain is going to be, we have the first one, which is going to be let me simply say, the proving or simply the derivation for the integrated rate law as far as zero order reaction is concerned. Then we are going to take a look at the graphical representation of what of zero order reaction. Then I'm going to talk about the half-life, right? I'm going to talk about the half-life of zero order reaction. Then we go ahead and move to some questions involving zero order reaction. We're going to solve some questions there, right? So now let's just start with the derivation of zero order reaction, that is the mathematical derivation of zero order reaction. It's very, very simple though, but you just have to understand the mechanism behind it. That's all. Now, suppose we have a reaction that occurs between reactant A, right, and it proceeds to give what? Let me simply say a product B, right? So one thing that you guys need to understand as far as rate of reaction is concerned is that rate of reaction actually deals with the speed, or simply let me just say with the rate at which a reactant is being converted to product. That's basically what rate of reaction is talking about, right? And then in order for us to actually evaluate the speed at which a reaction occurs, we have many things to actually deal with. That is the factors that can actually affect the speed at which this A is being converted to B, right? Now, as far as this is concerned, one of the things I would like to talk about is actually what the time, right? One thing we know is that the rate is actually greatly affected by time. The time at which it takes A to be converted to B, right, at a particular time is like whenever there is change in that time, the amount of A that remain at that time will be different. What I'm saying is that let's basically consider before and after, right? So one thing about A is that before A actually got converted to B, A is going to be present at a certain amount, which I'm going to represent as A, right? But one thing is that before the reaction actually occurs, B is going to be in an unknown amount. And the reason why is that we do not know the amount of B. Or let me just simply say, the amount of B is not yet produced because A has not undergone the reaction. Don't forget we said before here. Before the reaction actually occurred, that shows that B has not been produced at all. And simply, I'm going to represent the concentration of B to be 0. Then, after a particular time, that is, after A undergo the reaction, that shows that the concentration of A is going to reduce, right, by a particular factor. What I'm basically saying is that if we represent the factor to be X, that shows that A is going to decrease by factor of X. And the factor to which A actually decreases is going to be the one that is going to be produced as far as B is concerned. That shows that after the reaction, unknown amount of B will be produced, which are represented as X, while unknown amount of A will be reduced from the concentration, from the original concentration of A, which is this one that you're seeing here, right? And what that implies is that before the reaction and after the reaction, time actually is affected. Or simply let me just say, time, we actually need to take the time into consideration in order for us to determine the rate at which A converts to B, right? And we know that whenever you're talking about rate, we are basically talking about change in concentration with time. That is, change in the concentration of this A with time, right? So one thing is that if I'm going to write the rate expression for this reaction, which is actually the zero order reaction, what I would like to do is actually to bring out the rate. The rate is basically equal. Now, if you are writing the rate expression with respect to this reactant, that shows that we are going to be considering the mole ratio of the reactant. And in this scenario, I'm going to represent the mole ratio of A. I'm going to represent it as P, right? Then I'm going to represent that of B as Q, right? So if I'm going to write out the rate expression, that shows that the rate is going to be is going to be negative 1 over P, right? Then change in concentration of A, right, divided change in time. What it basically means is that I want to write out the rate expression for this reaction, and that simply shows that This negative indicate that it is reactant, and reactance is going to decrease it with time. Then the reciprocal what of the mole ratio is I'm going to multiply it what by the concentration of what of A. That's exactly what I'm going to have. Then this is going to be equal. If I'm writing the rate expression with respect to the product here, that shows that I'm going to have what? I'm going to have positive, right? I'm going to have this to be positive 1 over Q, right? Then multiplied by what? By change the concentration of what? Of B, right? Divided by what? Divided by change in time. Right. So, but one thing is that to study the rate of what of the reaction, we always take the reactant into what into consideration and not the product, because the reactant initially before it undergo a chemical reaction, you are going to know the concentration initially. Then after it's undergo chemical reaction, you are going to know the concentration of the reactant that remain. So truth be told, the concentration of the reactant, whether it is the limiting reagent or the excess reagent, actually determines the concentration of the product that will be produced at the end of the reaction. Do you get it now? Now let's just go ahead and simply write out the rate. So here we are going to have this to be equal. Now since we have rate equals to 1 minus negative 1 over P multiplied by change in A divided by change in T. So what we are going to basically do is that we are going to have this multiplied by this K. This K is actually the rate constant. That is the rate at which the rate constant at which A is being converted to B. Then we are going to have this to be multiplied by, if we are going to take the concentration of A into consideration, that shows that we'll be taking the equilibrium concentration, which is A minus X, into consideration. And that shows that I'm going to have A minus X all this power what? 0. And the reason I'm raising this power of 0 is because the reaction is actually what is zero order reaction, right? And that shows that I'm going to have it to raise power of 0. Right. So in that scenario, now what I will be doing here is that if you guys take a look at it very well, I'm going to equate the concentration of A and B together, right? But it's going to be the equilibrium concentration of both the reactants A and the product B. Now look at this. If I'm taking that into consideration, I'm going to be equating this and this together, right? So that's exactly what I'm going to be doing here. So that shows that I'm going to have here, if I'm considering this, let's just imagine that the concentration of the mole ratio of B is actually 1. And in that scenario, that shows that our Q is 1, right? And if our Q is equals to 1 divided by 1 is still 1. So that shows that I'm going to have change in instead of writing B, I already know that the equilibrium concentration of B is X. Then I'm going to put down X here, right? Change in X divided by change in T, right? This is equal. I'm going to have K into bracket 0. This is going to give us A minus, this should be A minus X all this power of 0, right? So in that scenario, what I'm going to be having here is actually what I'm going to have change in X divided by change in T. This is equal K, right? So since it is the rate constant for 0 order reaction, I'm going to indicate it with 0 here because it's 0 order reaction, of course. So now let's just go ahead and separate, because we call it integrated rate law, and that shows that we have to integrate actually, because it is actually used to determine the concentration of reactant at a particular time. That's the reason it is called integrated rate law. So now if we try to separate this, we are going to have change in X to be equal. I'm going to have this to be K naught change in T, right? So since it is integrated rate law, I'm going to integrate both sides. So if I'm going to integrate both sides here, I'm going to be integrating with limits, right? And that shows that integrating this with limit simply means that X is the concentration of the reactant, and that shows that I'm going to have A initial, which is A naught. That is if you remember, if you recall, the first concentration of reactant that we have is actually A, then A naught, and also A final, which I'm going to represent as T here, right? So if I'm representing it as T, the next thing I'm going to be doing here is actually to integrate this as well with T naught, and also with time T. So integrating this D is going to cancel this integral, right? Since they are opposites of each other based on integration and also the differentiation. That shows I'm going to have X, right? Ranges from we are going to have A naught here and also AT here. This is going to be equal. If I'm going to integrate this, I'm going to have K naught T if I should integrate it, right? Because D is going to cancel this integral, then I'm going to have K naught T. That's exactly what I'm going to have, right? So the next thing I'm going to have is that I'm going to go ahead and fixing the value of this X that is the limit value of this x. So that's what I'm going to do. So in that scenario, if I'm going to fix in the value fixing the value of this x, I'm going to have this to be I'm going to have it to be a final, which is 80, right? Then I'm going to have minus a initial, which is a naught, then all into brackets. I'm putting negative here, right? Because if you remember very well, when we say we want to equate the concentration of the product to that of the reactant to that of the product, there is negative. Actually, negative result is there, right? So this negative, I'm going to bring it out, and this is negative that's here. Then this is going to be equal. We are going to have this to be k naught into bracket t minus 0. That's exactly what it means. That is when time, we have to integrate our k naught with its limit as well, which is t0 and also t. So this is when the time is equal to 0, which is the initial time, and this is when the time is actually t, when it is the final time. Right, that's exactly what you have. So the next thing I'm going to be doing here is just to go ahead and let me simply simplify, right? So let me just simply simplify this expression to see what you are going to have. So from there, right, if I use negative to multiply this side, I'm going to have this negative a of t, which is the a final. Then I'm going to have plus the a initial, which is equals to, this is going to give us k naught t actually, and this multiply this is going to give us 0, right? So no doubt about that. So now let's go ahead and rearrange. If you go ahead and rearrange this expression, we're going to have this to be negative a of t, that is a subscript t. Then this is going to be equals to k naught t, right? Then minus a naught, right? This is the initial concentration. Don't forget why this is the final. So don't forget as well. So now the next thing we're going to do is just to go ahead and eliminate this negative sign in front of this final concentration. So if you want to eliminate it, we are going to have this to be a of t, right? Then this is going to be equal. We're going to have a naught, right? Then this is going to be minus k naught t, right? That's exactly what I'm going to have. So the next thing I'm going to do is just to go ahead and rearrange very well. So I'm going to, if I rearrange this very well, let's see what I'm going to have. Right? Let's see what I'm going to have. So rearranging this very well, I'm going to have this to be, we're going to have to be a of t, which is the final, equals to negative k naught t. Then I'm going to have plus a naught. So if you look at this very well, this particular equation actually resemble the this equation of linear equation actually, right? Equation of graph, linear equation of graph, and that is actually y equals to mx plus c. So from this, you should know that the y is going to be the a final, which is a of t, right? Then the m is going to be equals to that's going to be negative k naught. That shows that the slope of this graph, if I'm going to represent it graphically, that shows that the slope of this zero order reaction is going to be is always negative, which is k naught, right? That's negative that you're seeing here, which is the slope. Then that shows that if I'm not plotting the graph of x against x, the y is going to be, let me just stop this one, right? So that's so that the y is actually the dependent variable here, and that's a naught. That's what I'm going to be plotting the concentration of a final here, right? I'm going to plot it to that of x. X is actually t, which so that this rate actually depends largely on the time. So we are going to have the time here, right? So the slope is going to is going to be negative k naught. So the intercept here is going to be is going to be a initial concentration, which is the intercept, right? So it can also affect the value of this final concentration, right? And that's the reason I call it the intercept, right? It's intercept the reaction. So from there we have m to be negative k naught, which is the slope. That is the changes that this concentration actually undergo, which is actually the slope. Then we have the time, right? It's actually the t. So this actually the graphical representation of this zero order reaction. But one thing I want you guys to understand is that zero order reaction, for zero order reaction, we actually have x to be equals to k naught t, right? And if you look at this expression very well, before we actually integrate it with the limit, you find out that this x does not depend on the initial concentration of the reactant, and that is actually the major fact about zero order reaction. Zero order reaction does not depend on the initial concentration of the reactant, right? And that's very, very important for you to understand, right? So that's the main point and the main fact behind it. It does not depend on the initial concentration of the reaction. So that's it. The rate, to be specific, the rate does not depend on the initial concentration of the reaction. So now let's simply move to the last one, which is actually the half-life. before we start solving some question, right? It's very, very, very important. Before we start solving some question, we have to move to the half-life. So one thing I want you guys to know about half-life is that half-life is actually the time it takes a particular concentration of the reactant to reduce to what half its initial concentration. That's what half-life is. This is the original concentration, right? So this is the half of what of the original concentration. The time it now take A to reduce to this half is what it is refers to as half-life, right? That's exactly what it refers to as half-life. And half-life, that shows that the concentration of the reactant, right? The at half-life concentration of the reactant is going to be equal concentration about A over 2 is going to be reduced to half. That's what it means. And from there, the time is going to be what? Is going to be T half. So do you know what it means? What it means is that from this expression, x equals what? K naught T. I will basically be replacing my x with what? Concentration of the reactant divided by 2 because it is half. So that shows that from this expression that you are seeing here, from this expression, I'm going to have x to be equal to what? Concentration of this reactant divided by 2. Then I'm going to have the time to be equal to what? T half, since I'm talking about what? Half-life. So let's go ahead and fix all these parameters to this expression. So that shows that we're going to have for x, we are going to have concentration of A, right, divided by 2 is equal, we're going to have K naught T half. That's what we are going to have. So this is the first expression I'm bringing out. Then we just have to simplify the first expression further so that we can actually have the formula, right? So we can get the formula. So now let's go ahead and do that. So since we have what concentration of reactant divided by 2 equals to K naught T half, that shows that we're going to have concentration of this reactant to be equal to K naught T half. Then since I'm talking about what T half, which is the half-life, I have to make the half-life sort of formula. And that shows I'm going to have T half equals what? I'm going to have concentration, right, of this reactant divided by what? 2K naught. So this is basically what the half-life for the reaction. That is the half-life for zero order reaction. So and don't forget what I call half-life. I said half-life is what is the is the time it takes the concentration of the reactant to reduce to half its original size. Let me say half its original concentration. That's exactly what half-life is. So in this case, what's going to be the A naught? The A naught is going to be what? The original. That is going to be the initial. That is original concentration of the reactant. So that's A naught, and it is the initial concentration, not the final concentration. At this point, we are trying to talk about original concentration of the reaction. Original concentration of the reaction is going to be the initial concentration of the reaction, and that's why I'm having A naught here. So once the time is taken the A naught, which is the original value or original concentration of the reactant, to reduce to half its original size, is actually referred to as the half-life. And as you can see here, if there is increase in half-life, right, that shows that there will be decrease in. That's exactly what it means, right? So if there is increase in half-life, right? If there is increase in half-life, that shows that there is increase in the initial concentration of the reactant, and that's exactly what you are seeing here. Now from there, what I'm going to talk about is that the half-life of zero order reaction actually depend on the initial concentration of the reaction. Because if there is increase in the half-life, there is also increase in the initial concentration of the reaction, right? So that's exactly what. So that shows that the half-life of zero order reaction depends on the original concentration of the reaction, which is also known as the initial concentration of the reaction. Now, as far as this expression is concerned, this expression was actually the expression for the let me simply say zero order reaction. And what it means is that the rate of zero order reaction, the rate does not depend on the initial concentration of the reaction, as far as what you are seeing here is concerned, right? But as far as the half-life is concerned, that's as far as the half-life for a zero order reaction depends on the initial concentration of the reaction, and that's what you are seeing here, right? So now let's just move to some calculation. So the first question I'm going to be solving is actually this one that you're seeing here. The question says if a zero order reaction has a rate constant, and that's the first thing we are giving. The first parameter we are giving here, the rate constant, is actually 0.03. We have mole per liter per second, right? Then, and it takes 60 seconds for the concentration. It takes 60 seconds. This simply represents the time, right? So that's that the time is actually 60 seconds, right? Then for the concentration of the reactant to decrease, I'm going to represent the what this concentration of the reactant to be what to be A, and that shows that I'm going to have concentration of the reactant, which is this, which is equals to, we have it to what 0.9 mole per liter, right? Then that shows that this is actually what the initial concentration of the reactant, which is 0.9 mole per liter, then to 0.0 mole per liter, which is actually what the final concentration of the reactant, and that's 0.0 mole per liter, right? Then verify the rate constant by using the integrated rate law. So we are asked to verify the rate constant if the rate constant is actually right. So what we are going to be doing here is also to verify rate constant, and that means we are not going to be using this rate constant here, right? So from there we can actually recall that as far as integrated rate law is concerned, the expression for integrated rate law is given as, we have it to be, that's going to be concentration of A, right? That's final A to be equal, we have concentration of A naught, right? Then minus KT. That's exactly what you have. That's exactly what you have. So from there, what I'm going to be doing here is actually to go ahead and, let's say this is going to be here. We are going to make K the sort of formula. So if we make K the sort of formula, we are going to have this to be concentration of A substitute T, then minus concentration of A, right? So that's what we are going to have. This is going to give us equals what minus KT, right? Then if I go ahead and rearrange once again, then that shows I'm going to multiply everything. I can actually divide by this side by by T, right? So if I divide this side by T, I'm going to have this to be equals to K. If I rearrange everything, right, I'm going to have K to be equal concentration of A naught, right, minus what minus A of T, right? Then divided by the time. So that's exactly what I'm going to have. So I'm going to put all these things inside into this parameter. Let's see what we're going to have if I put it inside inside the parameters. So what we are going to have here is going to be this is going to be K, which is equal. We are going to have the initial concentration of the reactant is actually given as 0.9, and it is here, right? So we are going to have it to be 0.9, then minus this is actually the final, right? And that's going to give us we are going to have it to be 0.0. It is here, right? So I'm going to have this divided by T, which is the time. The time is actually 60 seconds, right? So we're going to put it there. So if we go ahead and solve this, 0.9, this is going to give us 0.9 divided by 60, and that's going to give us here we're going to have it to be, let me say if we are not using a calculator, we're going to have this to be 9 multiplied by 10 raised power minus 1, and this is going to be divided by we're going to have 6, right, multiplied by 10 raised power 1 actually. So if you bring this to the top, we're going to have everything here to be 9 divided by 6 is going to be this 3 goes in this, that's actually 3, right? And then 3 goes in this, that's 2. Then 3 over 2 is actually 1.5. So I'm going to have this to be 1.5 multiplied by 10 raised power minus 1, and this simply 1.5 times 10 raised power minus 2. Now if you look at this is 1.5 times 10 raised power minus 2, then we're going to have mole per liter per second. So if you look at this is actually the rate constant, and it doesn't it is not the same thing as this. If you look at this very well, so that shows that the rate constant is actually it doesn't match the calculated value. That's it, because the question says we should verify the rate constant. That's what the question says. We are asked to verify the rate constant. But if you look at this very well, since the rate constants are not matched, the value here is different from the value here, and that simply shows that there is actually maybe let me just say inconsistency with the data, or let me just say if the there is like maybe some mistake, there's some mistake with the data. That's exactly what happened, because the rate constants are not the same. So since the rate constants are not the same, that shows that we cannot just conclude that it doesn't obey the zero order reaction, right? But that shows that we can only say maybe the concentration of the reactant is actually there is, let me just say there is inconsistency with it. That's exactly what happened, right? Or let me just say there is mistake with the concentration of the reactant, and that's just it. So let's move to another question.